So today we will do some lower bounds. At least not today, but at least for next few lectures, we will be doing some lower bounds. So okay, so we will be doing some general methods to prove these lower bounds, and the idea will be that there are two kinds of lower bound that are proved in streaming algorithm. One are compression based, lower bounds, and second is communication complexity based. Okay, so in fact, it's not that the compression based lower bounds and communication complexity based lower bounds are different, but actually I would just say that let's say first, so compression based technique is one of the method which is also used for communication lower bounds, And these are basically, I would say, let's say, a pigeonhole principle kind of lower bound, PHP based lower bound. Okay. So the plan is that we will be doing distinct elements, lower bounds on distinct elements. Just 1 second. Okay. So for disjoint elements, and we will be doing more stuff when we get to communication complexity lower bounds. Okay. So let's see what the problem was. Long time back, we studied this disjoint elements problem. And what was that? So we had this stream x1 to xm of integers in the range, say 1 to n. Okay. And our idea was, the objective or the goal was to count number of distinct elements. Right? And for this, what did we see? So we saw that if T be the true number of distinct elements, then what we gave, then we used non-trivial low memory algorithm, use non-trivial low memory and non-trivial low memory and algorithm that used randomness and output and estimate T tilde. What was the property? Satisfying the following property. Probability that T minus T tilde is greater than epsilon T is less than delta. Okay? For some epsilon delta in open interval 0, 1. Okay? And there was an algorithm which depended on if you like space by some log n, and there was some function of epsilon delta. So if I recall correctly, it was some 1 over some epsilon big O of 1 log 1 over delta times log n. Okay. Now, so the two things we used. Okay. So the question we asked, okay, so there are three questions we can ask here. Do we need both approximation and randomization? Could we have randomized exact algorithm that fails with, say, probability, with small probability? Delta, or deterministic approximation algorithm? Okay. And unfortunately, answer to both these questions, all these questions, or answer to last two questions is no. And this was already proved by AMS in 99, Alone, Matthias, and Zigidi in 1999. Okay. So our idea today is to answer these questions via this method of compression. Okay. So first, let's show strongest possible algorithm is not possible. Okay. So what I'm going to show now, that strongest possible guarantee is not possible. And what I mean by that, algorithm that is both exact and deterministic requires omega n bits of memory. Okay. So our template is going to be, so what our template is going to be the following. Okay. This is our template of showing lower bounds. So what are we going to show? Suppose there exists an algorithm A that uses small memory, say S bits. Okay. Now, with help of this, we are going to give a function which we are going to call encoding from this to 0, 1 to the power GS. Okay. I'm going to, okay, sorry, some set A, this function. Okay. So what is the property of this function? First, this is injective, meaning encoding of X is not equal to encoding of Y if X is not equal to Y in A. Okay. So if two strings in A do not map to the same string in G of S, then what does that implies? This implies, what can we say then? Then we can say that, look, this implies that the G of S must be greater than or equal to log base 2 of cardinality of A. Okay. And now notice this only depends on this only depends on G, and hence would imply lower bounds on F in terms of log base to A, right? So our whole template will be that we will use this algorithm to come up with a function which we'll call encoding from a set A to some 0, 1 to the power g of s. But the only property of this function will be that it will be an injective function. Okay, it means two elements in A will map to distinct elements in our range. Okay, which implies that the size of g, like, or the g of s is greater than or equal to log base 2a. Because look, what is the meaning of this? This basically means that 0, 1 to the power g of s contains image of A, right? Now, since image of A are distinct, it implies that the image of A is less than or equal to 2 to the power g of s, right? Which implies that, and I know that what is the size of image of A? It is size of A, right? Which is less than or equal to 2 to the power g of s, which implies that g of s should be greater than or equal to log base to A. So this is just simple principle which follows from the injectivity of our encoding function. Okay. Okay. So next question is, so this is the kind of argument we will use. Why is this called a compression argument? Well, so basically this is called compression argument because what it basically says that if there exists a streaming algorithm that is too good to be true, then we can compress a large set A into a smaller one, right? Now, one more intuition is that why compression? But if you notice that most of the sketching algorithm or the streaming algorithm we made, what does it keeps? So you have this stream going on, right? It keeps a small sketch or small memory of the whole stream, and can recover the answer from this small memory. Okay, so in some sense, the streaming algorithm are by nature a compression algorithm. It compresses a big data into a small data and is able to retrieve answer from that data. So it is natural that if we would like to have a lower bound, then we should be able to exhibit a set A for which our algorithm cannot compress, right? And hence coming up with a lower bound. Okay, so is the overall scheme clear? Okay, and now we will exemplify this scheme on distinct elements. Okay, so the theorem we like to prove, this is our first theorem that we would like to prove, is the following. Suppose A is a deterministic algorithm deterministic algorithm, of course, streaming algorithm. Okay, that computes the number of distinct elements exactly. Okay. Then A uses, let's say, at least n bits of memory. Okay.
So, Saket?
Yes.
So you're allowing insertions and deletions, right? In
Yeah,
the
any streaming algorithm.
and n is the range of the elements, correct?
N is the range of the elements. True.
So I'm trying to think: is there even an n bits upper bound algorithm easy to see?
N log m is easy, right?
Log n is easy. Yeah, yeah,
N log m is easy.
yes, right.
Right?
And if you just have only insertions, maybe even n bits is easy.
Yeah. So what we will have is only insertion actually. So this lower bound will work just for insertion also. And if you have a lower bound for insertion, then you also have a lower bound for insertion and deletion.
Yeah. Okay.
Okay. So the way our algorithm will construct this sequences or this set A, it will only assume that my A is like the sequence. Look, the way we will construct our algorithm or the make our set A, it will only assume that A is is an algorithm which works for insertion. So we could have said even more stricter that even for the insertion only stream, this we have n bits of memory. But as you say, there are like of course there is a gap of log m. And why did you say that if I just have insertion only, then I can do, yeah, look, no, n bits is easy, right?
If you just have insertions, yes, because I just say an
Yeah,
element present or not.
yeah,
But if
and
you also have deletions, then I can't be sure.
yeah, so this will also work. This will work in yeah. So yeah, I know. Yeah, so this will also work for like for the deletion. The only upper bound probably we know in exact setting is this n log n bits or m log n. Yeah, the like it could also be the number of distinct elements are small. So there is also a lower bound. Like we can also design an algorithm where the data structure is proportion to the number of distinct elements.
Right. Yeah.
Right? We only keep if it is distinct, for example. So you could have a min of, I think, m log n and n log n, some such things, right? But as you just pointed out, at least for insertion only stream, this n bits of memory in exact setting and deterministic setting is tight. Okay, any other question? Okay, so what we will show uh, is that existence of A implies an encoding function from, we will give actually from 0, 1 to the power n to 0, 1 to the power s. And this will imply that s is greater than or equal to n. So now, how do I define injection? Okay, so what will we do now that you are given a string x in 0, 1 to the power n? I'm going to look at this algorithm A. This is my algorithm A. What is an input to this algorithm? Right? Some integer between 1, 2, 3 to n. This is what the stream is. So now given this, I'm going to make a stream as follows. So suppose I have, for an example, let's suppose we have 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1. Okay. So you just decide some. So first I'm doing from left to right. So this is like which position? This is 1. So I write 1. This is which position? Second. 3 is 0. I don't care. Fourth is this. Fifth, sixth, seventh, eighth, I don't care, 9. So I'm going to give to this algorithm the sequence 1, 2, 4, 5, 7, 8, 9. Okay, so this is what I'm going to feed. So basically what I'm going to do is that I'm going to order my x in some order and feed the stream I for which xi is equal to 1. Okay, so is the encoding clear? Like, is the what we are going to feed to A, is that clear? Right? So given x, I'm going to make this string and I'm going to feed A this string. Okay, now you just decide which way. Maybe you could have also counted 1 from this side and it would not have mattered. Just decide which way you want to choose. Okay, now what I'm going to do, I'm going to run this algorithm. And so let's call this, so encoding of x is nothing but, let's call this, whatever we created the string, x tilde, is a memory content of, what is the memory content of A when run on x tilde. So this is what my encoding of x is. So given a string x, I make this string x tilde, I run my algorithm, and at the end of the algorithm, what is the memory content? Or what is the sketch of the string which it has kept? I go and return that. I keep. So this is my function. So this is my end of my function. Okay? Now, how I'm going to show to you that this is injective? Okay? Is the mapping clear? In one piece. Okay. Now we would like to show that encoding of x is injective. What I'm going to do is we show that we can invert it or decode it, however you want to call it, via some inverse function decode. Okay? Now, how will we define this? Okay. So what are we going to do is that we are going to, so suppose you gave me some m, okay? And suppose this m is nothing but some encoding of x, okay? This is what it is. Now, this is what is stored. Now, from here, what is my goal? I want to decode, I want to find x, okay? Now, what I'm going to do, I'm going to decode this x, code x bit by bit, okay? Now, this is, so what do I, if I, from m, what can I compute? I can compute f0 of x, right? Number of distinct elements of x. Right? This I can compute. Now, what I will do now So this I know. So what is my F0? So let's not call it F0 of X. Let's call it just F0. Okay. So from M, I compute F0. Okay. Number of distinct elements in whatever this is of X. Now what I will do, I'm going to M1, M2, M3, or basically think of this way that on A, you had run some string that you would have got M. Now I go and feed 1. Then suppose I'm going to get M1, like content of my streaming algorithm A. When, look, think of this is that some state, like what is M representing? This M is representing some state when some stream was fed to my algorithm. Now I feed 1. I'm going to get M1. I feed 2, right? Then I will get M2, so on and so forth. So so what information, what do I have now? I have M, I have M1, I have M2, I have Mn. Okay? Now from M1, right? So what happened? So I had some string X tilde. Now suppose I put 1 and then I got the memory content M1, and from here I can get the value of F0 of X tilde 1. Okay, this is what I can get. Now what could be the value of F0 of X tilde 1? Right? So looking at M1, what can I get? I can either get, so let me use the F0 of M. Otherwise it will become, okay. So now what is of M1? Either it could be equal to F0 of M, or it could be equal to F0 of M plus 1. What can you say? When will this be equal to F0 of M? Anybody? So reading M1, like, so what I have done, so some string was there, I appended 1 to it and said, okay, now what is your memory content? Now I ask myself that, oh, what is the number of distinct elements of this particular string? Either it could be same as before, or it is 1 extra. When it is same as before, it means 1 was already present in X tilde, right? In which case, what do I know? Right? That's the only reason why. So I know that the first bit here is going to be 1. Right? And if this is F0 of M plus 1, it means this bit was not present there. It means, or 1 was not present in X tilde. That is why the number of distinct elements has increased by 1. In which case, if this comes, then if this comes, you set 1. In this case, you set 0. Right? So in either case, so now similarly, next I will look at M2. I will check whether the second bit is set to 1 or 0. If the number of distinct elements remains the same, it means this number was already present in X tilde. Okay, fine. Then I set it to 2. All right. Then for that bit, I set it to 1. Oh, if the number of distinct elements increase by 1, I set this bit to be 0. And this is the way I can reconstruct my X from the set of informations M1 to Mn. Is the decoding algorithm clear? Anybody? Okay. So, and notice that this way of decoding, right? So what is the meaning of this? What we have been able to show because of this, that two strings will not be mapping to the two strings of X cannot be mapping to the same string in Y, because if their memory content will be same, we cannot distinguish between those two different strings, right? Because this procedure is a unique way of decoding some objects. Okay, so this guy is only going to give me one particular string. Okay, so if what does this imply? Suppose x1 and x, yes.
Sorry, could you repeat? Where are we using the fact that the encoding was injective?
No, we are proving here that the encoding is injective. Okay. This is the decoding procedure told us the encoding is injective, because this decoding procedure literally inverts the, like it's just an inversion function, right? It literally takes the content, because it is a deterministic algorithm, right? So because I'm only running the content of this deterministic algorithm, I cannot be making a mistake of f0m and f0m plus 1, right? So what it means, so suppose you had two strings, x and y in 0, 1 to the power n, right? xy in 0 to the power 1 to the power n. Suppose this is what it was. Now, I know that if x is not equal to y, if x is not equal to y, number of distinct so suppose x is not equal to y, there are several cases, right? I mean, I do not want to do it, but if you ask, this is what, so if you take any x and y, right? There are some places where they will differ, right? So basically, you can think of xy in 0 to the power 1 as basically some subset of n, basically where, what is a subset of n? Is basically those position.
Yeah, the characteristic vector can be looked at as a subset. So
yes,
x and y.
which I said to him. Okay, so now, like, so I fed them. I get this. Okay, now I fed, I fed another one. I know as a set also they are different, right? So I fed them and I got, say, m and m. Like, this is what the memory content. If they are same, okay, if they are same, now this set has gotten from some x, this set has gotten from y. Okay, now I asked, what did I do as a procedure? It's a deterministic exact algorithm. I asked myself that, okay, fine. I look at my m, I gave 1. I look at m and I gave 1, right? Now, in some sense, or look at a number which is present in one and not present in other. Okay, there will be some coordinate which is present here, which is not present here. Suppose that is I. So I is present in X. I is not present in Y. Suppose this coordinate is not there. Like one is 1, other is 0. Now, if I give Mi, right? It's a deterministic algorithm. From here, what can I say? What can I conclude from Mi? Oh, so look at this string X and you feed I. Now it was M, so it's a deterministic algorithm. Now it has got some letter I. The memory content can only become some Mi. Okay, whatever that means. Okay, and here also, if the memory content is M, it's a deterministic algorithm. It can give me only Mi. Now it's a deterministic algorithm, then I should be able to get an information from this Mi and this Mi, what is the number of distinct elements are there. Now in one, if M would have been same, deterministic algorithm will say same in both case, 25 say. Here also it has to say 25. But I know X has, I was present in X, so it is 25 is correct, but I is not present in Y, okay? So it should be 26. But so a deterministic algorithm cannot be giving me wrong answers. So this is why you are getting a contradiction that, well, I mean, if you had a 2 string, then whatever you are going to encode, it has to be distinct. Otherwise, you must be getting a wrong answer. But that is one way of proving it. So this you can also prove this way. But the other way is that you give a deterministic algorithm to decode an object. Because once you have a deterministic algorithm to decode, and your algorithm was deterministic, this function becomes invertible. And if it is invertible and it's a unique inverse, it means the function is injective. Okay, so this is another way of saying it. Okay, so basically exhibiting a decoding function is good for us to show that it is an injective function. Okay, so now I would like to go ahead and I want to say that no deterministic approximation. Okay, so what I'm interested in, suppose I'm happy with 1.1 approximation. What I mean by this is that, okay, I'm happy, suppose n tilde is distinct element, you return me some number between this. I'm very happy. So if n tilde is the number of distinct elements. Okay, now I'm interested in what? Deterministic algorithm. Okay, so I still would like to do the same thing. I would like to come up with an encoding function, some set A, 0, 1 to the power s. Okay, and if say A is large enough, suppose I say that A is my 2 to the power, say, n by 1000, suppose, then what can I say about S? Then that implies that S has to be greater than or equal to n over 1000 by the similar argument before, which will imply that we need an omega n space. Okay, even to do an 1.1 approximation. Okay, now, so the whole objective is to come up with such an A. Okay, now notice what we did earlier, that suppose A is going to be some subset of 0, 1 to the power n, or rather say this is going to be subset of some 2 power n. Okay, and so encoding is going to be the same. Encoding of x, now if I think of A at 2 power n, then encoding of x is like just x. Okay, okay. Encoding of x will be nothing but whatever the algorithm is. Say for this we have an algorithm D approximation. So memory content of D time x, no x tilde if I think of this. Now the question is, when in the decoding setting, okay, when in the decoding setting, what would I like to do? I would like to do, okay, so think of this way, that I had some x, okay, now, or let's say, okay, let's say I have some z here, okay, so suppose x is supposed to map to z, but what I'm able to get is some z tilde. Okay, like I'm not able to get z, but suppose I'm able to get something which is z tilde. Now, but from z tilde I want to recover x. Okay, from z tilde I want to recover x. So if somehow we could have a world where I could partition the world in some way, here, the mapping world, that in each of this partition, only one element is mapped. Okay, nobody else is mapped. And somehow, suppose I know, now, if something is false here, z tilde, then I map it back to X, because I'm saying that, look, the only way you can get Z tilde is something. Now, let's think about it. What is the meaning of being Z tilde? So, well, here, encoding of X is think of these numbers. Okay, think of these numbers, strings, and now think of these strings, and I have a 1.1 approximation algorithm. So it must be mapping from this content to something which tells him that, well, it is not too far away from here. Okay, which is like, I mean, it must be mapping this X, maybe not to a Z, but to a string which is close to Z, such that the Hamming distance between them is not too much. Okay, is not too far away from here. Okay, and this should remind you of, in some sense, of error correcting codes. Okay, so let me introduce. Let's take a detour and let me introduce this concept of, we will not use it, but it is important, I think, to know this. And this is why you will see that why these objects come so often whenever we talk about approximation. Okay, be it in FPT approximation, normal approximation, they come up every time, is because of the following reason. So an ECC, or error correcting code, C, is some subset of Q to the power L. Here, Q is the length of alphabet, okay, and alphabet size, length of alphabet, and L is the block length. This is also called block length. And Hamming distance between two elements of Q to the power L is the number of entries where they differ. Okay, and there's also a notion of relative Hamming distance. Which is basically delta xy divided by L. Okay, now there are two parameters which are very important for the code, something called distance of the code. Okay, which is minimum C, C prime, C. Okay, and another thing is relative distance of the code. Minimum which is basically D over L. Okay, and the main observation why these are important and interesting objects is because of the following. Okay, C has diameter D. Then the open Hamming balls of radii d over 2 about all C in C are disjoint. Okay? Okay. Now, what is the meaning of this? Let's try to understand what is the meaning of this is. Okay? Now, why it is important is that here is a ball around some C. Now, what happens is, okay, now why do the Hamming distance between them is small? Well, suppose you had some element here, okay, and the problem is that what happens if this guy also belongs to someone? So if this is not disjoint, then there is an element which belongs to both. Now look at this distance. This is less than equal to d by 2. It means number of places which this and this differ is at most d by 2. Number of places this and this differ is at most d by 2. This is what I mean by open. What is the meaning of x and what is the meaning of this C prime and C then? What can we say? This is less than d by 2 plus d by 2 less than equal to d, right? This is just basically triangle inequality. Okay, so basically what is happening is that all these balls are disjoint. Okay, now
a question, please.
yes.
I do not understand this statement. So what is the diameter? The diameter is the maximum shortest distance, right?
No, Feder. It's a minimum of every pair.
So it's not diameter, it's distance. Okay, yeah.
But yeah, it's the distance. Okay.
Okay, sorry.
I should have said. Okay.
You were saying diameter.
Sorry, this.
Okay. So this should be that. Okay. Now I got it. Yeah. Sure.
Yeah, my mistake.
Thanks.
Okay. So this is. So now, why it is interesting in the sense that, okay, so the way it is used in the coding world is that if you have an adversary, okay, think of this as a transmission, okay, and all the parties know the encoding function, okay, all the party know the encoding function in advance, okay. Now I take some string x, I apply my encoding x, and this is what it should go. But now what happens is that on the way, this channel is noisy, okay? So somehow encoding of x becomes corrupted, okay? And what is the meaning of corrupted? Some bits are changed. Okay, but notice that if it is number of bits that are changed are strictly less than d by 2, okay, then what I know, then I can correctly map it to the encoding of x, right? Because these are disjoint balls. So if the number of items which gets corrupted is strictly less than d by 2, because I know my encoding function, what will happen? These adversaries can say, okay, fine, channel has become noisy, it has got encrypted, but I can uniquely decide which element does it belong to. Because I have a guarantee that the number of places where it has changed is at most d by 2. So if I knew that what all my encodings are, right, for this set of strings, then I can know like exactly, but even if it is slightly changed, which one to go to. Okay, now imagine yourself. So how do you apply to streaming algorithm, or for that matter, any approximation algorithm? Is that fine? I know okay, I know these balls. Okay, now so like imagine that you have a 1.1 approximation algorithm. Okay, but if you knew that these points where these guys are mapped to are too far apart from each other, like really very far apart from each other, right? And so I know these points where the mappings could be, and the property of these mappings are that they are really very far apart from each other. Then even if you apply 1.1 approximation, think of this, that this bit has been corrupted some small fraction. Okay, fine. Even if you are corrupted small fraction, you are here. Like in some ball, you will not be part of two distinct balls, because then only the problem lies, because then I don't know whom to go and then whom to go, right? So if I could have an encoding function which maps elements in my range space in such a way that if I look at a ball around each of this place, if it is disjoint, then even if something gets corrupted, which is like applying our approximation algorithm, okay, I still can recover which element you might have been and then apply my inversion function to come back to it. Okay, so this is an idea which is exploited time and again, and we will also exploit this idea to do things. Okay, so I will not prove this, but I will not go via coding theory, but whatever I'm going to prove is still a coding theory. So what is known, the coding theory is a course in itself, and like a lot of things has happened. So what is known is that for any integer, q comma n greater than or equal to 1, there exists a code equal to n and block length L equal to order q log n, with relative distance 1 minus 6 over q. Okay, which basically means that the number of places that you match is roughly 6 over q fraction. Okay, most places you are disjoint. Okay, but what I'm going to prove is not, actually this is the proof for this, but not in this language. I'm going to use a set theoretical language because that is slightly easier to use in our setting. Okay, otherwise we have to translate whatever I'm going to prove into the language of coding theory, but we don't need to do it. But it is important that whenever you have an approximation, what is lying behind all this is a code. Okay, so even if you look at FPT approximation for that matter, or any approximation, like coding theory is all over the place. Okay, so what we need is this lemma, which I'm going to, so there exists a family, okay, C, subset of 2 to the power n, satisfying following property. Okay, first is that is greater than or equal to some 2 to the power some Cn, so it is exponential. For all S in C, cardinality of S is n over 100. So each set is of size n over 100. And third, for all S not equal to T, S intersection T is less than or equal to n by 2000, which is like mod S over 20. Okay, so what is this? They are of size n over 100, each set, and the pair by the intersection is very small. Okay. Okay. So now let's suppose if you would have given me this lemma, how will we rule out exact, approximate, or rather not exact, deterministic approximate algorithm for distinct elements. Okay, so my encoding function will be, so from this particular C, the lemma. Okay, so let C be from the lemma A. If you notice, this is basically code word, right? Because I could also think of this as a kind of strings, okay? And I'll get to that in a minute at the end. And then this is basically the code, and this is basically the proof of this theorem. But the translations requires going here and there, but that is basically we'll see the proof, okay? So look, we do not need to construct this. For our proof, all we need is such a good set exists, okay? So let C be from the lemma A. So now I'm going to give a function, encoding function, to some 0, 1s, okay? So encoding function is going to be same. Suppose you give him C in C. So what it is going to take, okay? So it's basically, your string is like C itself is the string, okay? Now, here's your approximation algorithm, D, okay? Now, you give it C, okay? And now, what will be encoding of C? Encoding of C will be memory content of D on C. That's it. So this is what I have mapped to. Now, suppose this is some Y, okay? Now I would like to give a decoding function. Okay, I like to give a decoding function, okay? So how will we give a decoding function? This time we are not going to construct these elements one by one, okay? So we will construct it slightly differently, okay? So I don't know which one it is, but I will show you that how we can distinguish between them. So now take some x in C, okay? For all x in C, we will do the following, okay? Now, here, suppose y is with respect to some set memory content of, so suppose, okay, here is some encoding of, say, some string z, okay? This is what is y is, okay, for some set z. Now for all x in z, what I'm going to do, I'm going to take the state of D, okay? So here's your D, okay? Now you pick x in C, okay? And you run z, x, okay? And like, so you have first fed z, which you don't know. Only thing you know that here's your memory content. This is only thing which you see is y. So now you have fed x, okay? So now suppose the memory content of this, I'm going to call it mx, right? For all this, okay? Now, from there, I'm going to ask myself a question. So first, looking at y, I say, hey, for y, what is the value of f0 corresponding to what you have stored? Corresponding to what you have stored. Okay? And suppose, then what are you going to get? So suppose, say, I'm going to call it f0 y. Okay? So then this is going to be, this is an exact value, suppose. Then what you are going to store is, I don't know, is f0y divided by 1.1 less than equal to okay, this is what you're going to get. Now, let's ask ourselves, what happens that x, so what is y? Remember, it is a memory content. It is basically encoding on z. So suppose, like I'm going through all the strings in C. So when I give x equal to z, what happens? So when I substitute x equal to z here, a number of distinct, now if you look at this mz, okay, notice that the number of distinct elements is going to be same, because basically we're appending z, then you are appending z. So the number of distinct elements are not going to be same. So then what you are going to get, in this case, you are going to get, and look, all the strings has size n over 100. So in this case, the estimate which you can get is n tilde is roughly n over 100 minus n over 100 and no, n over 1000, right? N over 1000. Now, but let's look at if the x is not equal to z. It's something very different. Then what you know, that z intersection x is very small, less than equal to n over, if I recall correctly, it was n over 2000. Right? But so in this case, basically you think of this, that I have here z and I have another x here who only shares small number of points. It means the number of distinct elements which they have is quite huge. So it's like roughly 2n over 100. Okay, so now you're going to get an estimate, in this case 2n over 100 minus 2n over another 1000. So this is your estimate in this case, and you're going to get 2n over 100 plus 2n over 1000. Okay, now look at this. When you will feed x equal to z, the number of distinct element is roughly n over 100. But when you will feed n over, but when you will feed z, which is something, then the number of distinct elements is going to be very different. Like it is going to be double. Like it is going to be double. It is like 2n over 100 roughly. Okay, so then basically, what you know? So looking at memory content y, okay, you are going over all x in C, right? Now, for whichever value, so for whichever x, okay, number of distinct elements is around n over 100, okay, what will you say? Well, it is this x for which y is encoding, okay? And for all others, by our construction of C, they're going to be closer to be more like 2n over 100, right? Which is too far away. So in fact, So this is it. That's end of my decoding algorithm, right? So I look at my approximation algorithm and I say, look, okay, now let me feed this X. Oh, if they are going to be same, number of distinct elements is going to be very going to be the same. So I'm not going to change my estimate by too much. But if I'm going to feed him some other string, which is different from X, then I know they differ at far too many places that the number of distinct elements will be just blow up. Right? So I can see the difference between number of distinct elements and decide, oh, if it is near 2n over 100, then I know this is not for which this encoding is. Throw this out. Again, I checked it. This is not what it is close to. Throw it out. And the moment someone becomes closer to n over 100, I say, yes, you are my encoding. And by the property of the code words, right? N is sufficiently large. By the properties of code words that we have made sure that our decoding is correct. Okay? Is the decoding algorithm clear? So basically, the only thing which we have to care is that, I want to know which X for which this encoding is. Fine. So I try all possible X for which this could be encoding. And the great thing is, if it is true, for the right X, the number of distinct elements is closer to n over 100. For the wrong X, the number of distinct elements is closer to 2n over 100. So now we have created this gap. For the wrong or for the no instance, it is like somewhere else. For yes, it is somewhere else. So this is the gap. So if my approximation algorithm cannot break this gap, then for all those approximations, we will be good. So for example, this guy, the same argument, if you notice, there's nothing about 1.1. We could have ruled out up to factor 2 approximation. 1.9 also we could rule out, right? Because up to 1.9, it is still closer to n over 100, right? 1.9 n over 100, right? Second one will be like more 2n. So there's still gap. So in fact, we can show using the similar argument that up to factor 2 approximation, it is 2 minus epsilon is not possible in omega less than omega in space. Okay? Any question? Okay. So now let's try to prove this lemma. This combinatorial lemma. Okay. So this combinatorial lemma proof is very simple, not very hi-fi. Okay. So what we are going to do, so I'm going to first say that 100 divides n. Okay. So I'm only for this. So what we're going to do, we are going to make a buckets. Bucket 1, bucket 2, and bucket L, where L is going to be n over 100, right? So it is like 1 to 100, 101 to 200, so on and so forth. Okay. So basically, my bucket bk is going to be equal to 100 k minus 1 plus 1 to 100k. Okay. And k is between, okay. So k is like n over 100. Like 1 to n over 100, right? Now, the way we will construct our C, in our C, we'll have the property that for all I in n over 100, C intersection Bi is going to be exactly equal to 1. Okay? So what is the construction? Construction is very simple. Okay, so I'm going to define a set C uniformly at random select an element from each bucket. Okay? So this is how C. And how many such C will construct? So we'll construct C1, C2, CQ. Okay? So we will see how many we can do. So this is how we will construct, right? So we will construct Q such sets where each set Ci is constructed by picking one element uniformly at random from each of the bucket. Okay? Okay. So now, let's say, what is an expectation of Ca intersection Cb for two distinct sets? Okay. So now what I'm going to do, you set up your random variable y a comma b comma j, right, is 1 if Ca intersects Cb intersects bucket bj is equal to 1. Okay. So from these bucket, it picks the same element and 0 otherwise. Okay. So what is the probability that y this is equal to 1? Well, so I have a bucket here and I have a bucket here. No, I have a bucket bj, right? Now, first set can pick up any of these elements. So it is 1 over 100. And bj picks the same elements. So that is 1 over 100. But it could be any of these elements, like of this. So you have to multiply with 100. So this is like 1 over 100. Right? So this is 1. If is like, so basically what is this? You either could have picked up the first element, both picks the first element. What is the probability that both picks the first element? 1 over 100 times 1 over 100. What is the probability both picks the second element? 1 over 100 times 1 over 100. And there are 100 such elements. So 1 over 100. Okay. Okay. So what is an expectation of Ca intersection Cb? By linearity of expectation, it is n over 100 times 1 over 100. It is n over 10 to the power 4. So two sets intersect on n to the power 10 to the power 4 number of places. Okay. So now what will we apply? We apply Chernoff bound. And say what? We apply Chernoff bound and say probability that Ca intersection Cb is, say, 5 times more than expectation, n by 10 to the power 4 is like roughly some e power minus Cn. Okay? Okay. So now I would like to get a bound on that. So this is all good, but I want to show that now I would like to apply union bound. Okay? I would like to apply union bound and show what is the probability that there exists a comma b in 1, 2, q such that Ca intersection Cb is greater than 5 times n over 10 to the power 4. Well, this is Q choose 2, right, times e power minus Cn, right? Now, so suppose I want this to be less than equal to 1. That implies if I show this less than equal to 1, so now this will give us a value of this. So basically Q choose 2 is like Q square e power Cn should be less than 1, which implies Q square should be less than equal to E Cn. So Q is less than equal to E Cn over 2, right? So if the number of sets we would have chosen is like roughly like something smaller than E Cn over 2, right? Then we are good, because what this implies that, well, there exist sets C1 to Cl such that for any, we know already that the sets the way we have constructed is n over 100, and first of all, secondly, we can, number of such sets we can create is roughly e power cn over 2. And secondly, the pair by the intersection is upper bounded by n over like some 5n over 5n to the power 10 to the power 4, which is much less than we asked in our theorem here. Okay, so this is just a proof from probabilistic method, right? So what we did, we constructed B1 to BL of size 100 each. Then we constructed CIs by picking one element from each BI uniformly at random. Okay, and how many such sets we created? Q such sets. And then we try to analyze the properties of these things. So first we upper bounded the intersection of these things, like expectation, which are like n to the power 10⁴. Then we threw Chernoff bound to show that probability that it will be far off from its expectation is like e power minus cn. Okay, because this is a probability for each pair, but we want this property to hold not for each pair, like for a particular pair, but for each pair in my sets. So I said probability that there exists a bad pair is upper bounded by number of such possible pairs times probability that each pair is bad. If that happens to be less than or equal to 1, then we will be good, because that implies by probabilistic method that there exist some codes with the desired properties. Okay, and we know that if we choose q less than or equal to some e power cn over 2, then we are good. Okay, so any question? Okay. Okay, so let me in whatever time I have, let me try to tell a little bit more some things. Okay. Okay. So there is also a theorem. Let me give you, I may not be able to give you complete proof, but let me still give you an idea. So can we have a randomized exact algorithm? Okay. So this proof came actually a little bit later. And this is by, okay, I think some, okay. So suppose A is a randomized streaming algorithm. That outputs the exact number of distinct elements with success probability, say at least 2/3. Okay, at least 2/3 for the last query. Okay, in any fixed sequence of stream. Streams, updates, and queries. Okay, then A uses Cn bits of memory for some C greater than 0. Okay. So how does the proof goes? Proof is quite interesting. First of all, I'm going to assume that the success probability, okay, is at least 10 to the power minus 6. Okay. Success probability or is at least 1 minus 1, or the other failure probability. I will tell you how to get rid of this requirement at the end. Okay, and it uses order S space. Okay, so if you started with S space with success probability 2/3, you can do it 10 to the power minus 6x, 10 to the power minus x 6 by just running them in parallel and returning the median and then applying Chernoff order bound. But for now, let's believe that this is what the success probability. So only algorithm which we know is to give encoding from some set A to 0, 1 to the power S. Okay. But now, how are we giving encoding algorithm? So now, if suppose this A is going to be, our A will be some subset of the phi that we constructed before. Okay, still large enough to guarantee the desired lower bound. Okay. Okay. So now what will we do about this? Okay. So our algorithm was that fine. If you recall, the algorithm was the encoding algorithm. What did it do? It ran encoding of some string X was basically memory content of A on X. Okay. And decoding algorithm was say decoding we did for bit by bit, or rather, okay, we'll okay, or return the encoding that is closest. Okay. Okay. But what is the problem with this if I do this now? Can I do this now? Can I define my encoding function as this? Anybody? Can I define it like this now? If I define like this, will it be even a function?
It's a probability distribution cycle.
Exactly. So A is a randomized algorithm, right? So if I define like this, based on what random string it takes, memory content could be very different, right? Because for randomized algorithm, right? So for randomized algorithm, right? For randomized algorithm, what happens? For randomized algorithm, algorithm is not only X, but some random string R. It depends on both. Then it is deterministic. Right? Once I provide both X, the real input string, as well as random string, then the outcome of this algorithm or the behavior of this algorithm is deterministic, but it depends on the random string, right? So since A being a randomized algorithm, I cannot say memory content of A on X, okay? So what I can do, so let's call this some encoding prime, and this is like decoding prime, okay? From here, we will get our encoding and decoding. Okay, so now what happens is that let's ask ourselves the following question. Okay. Okay. Now you fix some X in your C. Okay. And suppose some X prime is the random vector that we decoded. Okay, X prime is the random vector that we decoded. Okay. Okay. So suppose let yxi be the indicator random variable that says that ith bit was decoded correctly. Okay. Then or rather decoded incorrectly. That's better. So what is y of x? Well, I equal to 1 to n yxi. Okay. Then what is an expectation of yx? Is like, look, probability that one particular, look, so how we do bit by bit encoding? We say, hey, what is your solution now? What is your solution afterwards? We know that that's a failure probability is 10 to the power minus 6, right? So the expected number of this is going to be n over 10 to the power 6. Okay. So bilinearity of expectation. Okay. Then probability, suppose zx be the random variable for the event yx is greater than 2n over 10 to the power 6. So probability that zx is equal to 1 is less than equal to half by Markov. Agreed? Right? By what is that yx is more than 2n over, like the number of places that you have messed up is more than 2n over 10 to the power 6. It is, so if you apply Markov, this is less than equal to half. Okay. So basically what this means is that, so probability that decoding prime, encoding prime on some f is not equal to f is less than equal to half. Right? So as I was telling you, right? So any algorithm AX, deterministic, can or randomize, can be thought of as if and only if it is deterministic, but X and some random string R. Okay? Now let's set up an indicator random variable. What does it tell us? It tells us that let ZF is equal to 1 if decoding prime, encoding prime of F is equal to F, 0 otherwise. Okay. Now, if you take expectation over R, summation ZF, F in your C, what is this? This is greater than equal to C over 2. What does this implies? That implies there exists R star like a fixed, which is, so basically this tells us that look, one, if this, we know that each of this happens with probability like equal to F with probability strictly greater than half. So the number of strings, like number of sets for which, right, some particular string works correctly is like number of sets is like more than half. So you just fix this R star for which, you fix this R star for which number of sets is more than half of your sets on which, my decoding algorithm returns correctly. So now you do your encoding, decoding, everything with respect to this R star, right? So based on this, there is fixed R star such that if F runs encoding prime, decoding prime with respect to R star as the random string for A, then for at least by 2 sets, okay, we are great. Okay, so that's it. Then what I have been able to show to you is that there exists some set which is large enough for which this is good. So, so if you have a very low probability event, so what we are able to say, if you just go back here, so we first said that, okay, given X, let's define this encoding prime of X, okay? And then we said, whatever may be the X, whatever may be the encoding prime of X, decoding prime gives me, decoding primes fails at the number of places, it fails in like roughly n over 10 to the power 6 number of places. And for very few number of strings, it fails. And then what we said, okay, fine. So number of strings for which decoding algorithm succeeds for a particular string is huge. So in particular, same string succeeds for large fraction of my strings, encoding, decoding happens correctly. So now what I'm going to do is that rather than running my algorithm on like arbitrary just string, I'm going to also feed him this string and this particular random string and then look at the outcome, okay? And do encoding, decoding with respect to this. So basically what happened that with help of this randomized algorithm, we extracted a deterministic set on which my algorithm behaves more or less deterministically with respect to one particular random string, okay? And so if you did not follow this set of arguments, it is perfectly fine because these are very involved. This is very involved argument. And this is something which is used quite often nowadays to show lower bound even against randomized adversary or randomized algorithm. So, and I was also very fast in last 10-15 minutes, but I still wanted to give you a flavor of the kind of arguments people use to get a lower bound from a randomized algorithm. But what I would like you to take from this lecture is that like if you want to do approximate, like if you want to win against an approximate adversary, then you should think of code words and try to design objects such that the encoding function or the algorithms gives you answers in balls where things are far apart, so that if you your answer falls within this, then you can tell you're closer to which answer, and based on that, you can distinguish between distinguish of existence of particular kind of approximation of them exist or do not exist. Okay, so I don't think I wanted to say more today. And on Wednesday, we will do communication complexity based lower bounds on equality and index. But these are the lower bounds, which is quite general. And we will see some of these kind of things also used in getting a lower bound for the basic primitives in communication complexity. Okay, any question? Okay, if there is no question, then let's meet on Wednesday.